In this part of day 2's lecture, or the last part, we will discuss about the Charpit's method. Now, Charpit's method is used generally for nonlinear partial differential equation of first order. Now, say the equation given is in the form, this is a function of x, y, these are the independent variables, z, the dependent variables, which is depending on x and y, and del z del x, that is p, and del z del y, that is q, and the function of them is equal to 0. Suppose this is the given partial differential equation of first order, but which is non-linear. Now, what Charpit's method does, it introduces another partial differential equation of first order written as g x y z p q is equal to 0, but the condition is this g should be compatible with the given equation f. Now, what compatibility does mean, that we will discuss later, but previously, whenever we are solving these two, we will get p, that is del z del x, as a function of x, y, z, and a constant, say a constant means, say a constant a. Another equation we will get solving these two, that is del z del y, as q, which is a function of again x, y, z, and the same a, the same constant. So what we do, we write dz, the total differential of this, as z is depending on x and y both, so del z del x dx, that is the changes, rate of change towards the x direction multiplied with the differential coefficient, and similarly del z del y multiplied with dy. And as we know these two values, like x, y, z, a dx, and q, x, y, z, a, and dy. Now what we have to do, we have to solve this ordinary differential equation, and another constant will be evolved out of this integration. Now, question is, what compatibility does mean? Compatibility means that the necessary and sufficient condition between these two functions to be compatible is compatibility means that the Jacobian of fg for xp plus del fg for del zp, and a p will be multiplied here, plus del fg for del yq and del fg for zq, and a q will be multiplied there, and that summation will be equal to 0. So this is the compatibility condition that should be held, and whenever that should be held, if we write explicitly, this means del f del x del g del p minus del f del p del g del x, that is the first Jacobian we have written here. Now the second one, p multiplied with del f del z del g del p del f del p del g del z plus del f del y del g del q del f del q del g del y plus q del f del z del g del q del f del q del g del z, and that is equal to 0. This is the meaning of this summation of Jacobians is equal to 0. We have written there. Now what we will do, we will keep all the differentiation of f aside, and we will write it like, see, there is a del g del x there, so we are writing f p del g del x first, then we will find del g del y. Now there is the del g del y, this is coefficiented with f q. Next we will get del g del z, and the coefficient del g del z's coefficient is number 1 this one and number 2 this one. So f p, sorry, actually pfp plus qfq. Next one, we will choose among them del g del p, and the coefficient is del g del p's coefficient is there, a minus sign will be added, p f z minus f x. Next one, del g del q. Now there is a del g del q, so q f z minus f y from there, and this is equal to 0. No more terms has been left. Now see, this is like the Lagrange's equation itself, right? And so from there we can write the auxiliary equation as del dx over fp, dy over fq, dz over pfp plus qfq is equal to dp over minus fx plus pfz equal to dq over minus fy qfz. So this is the auxiliary equations of Charpit's equation, and we can use this equation, this formula to solve different differential equations which are of order 1 and but non-linear. So we will start by some examples. So I will keep this formula in my hand. Whenever this will be recorded, I will show this page. Okay, so first problem 1, p square plus q square y is equal to qz. Okay, now what we are doing, so we have actually this is equal to p square plus q square multiplied with y minus qz, and that thing is equal to 0. So we will firstly we will find all these coefficients such that we can solve easily. So fx is equal to, see, no dependencies on x, so it's equal to 0. Then fy, there is y, so p square plus q square. Then z, there is z, so fz is equal to minus q. Then fp, there is p, so fp is 2py, and fq, so this is 2qy minus z, right? So following this 2, now we will write the auxiliary equations dx over, it should be fp, and there is your fp, so there is 2x over 2py, and dy over, there should be dy is on fq, and this is fq 2qy minus z. Then dz, this is the form of dz, pfp, so 2p square y, and qfq, so 2q square y, 2q square y minus qz, and dp over this one, fx is 0, and pfz is minus pq, and dq is equal dq over minus p square plus q square minus q square. So from these two, at least, we see that we have dp over pq is equal to dq over minus of p square. So we get p dp plus q dq is equal to 0. Solving, we get p square plus q square is equal to a, where a is an arbitrary constant of integration. So now from equation 1 and 3, so I mean we will do this we will input this value in the original differential equation, and we have now a y is equal to q z, right? And so we can write that q is equal to a y over z. Now if q is equal to a y over z, then p square plus s square y square over z square is equal to a, and from there we can write p is equal to, neglecting the negative value, a z square minus a square y square over z square, and now dz is equal to p dx. So p dx is this big thing, a square z square minus, sorry, a z square minus a square y square over z square dx plus ay over z dy, right? So from there easily you can see this can be written as z, because this is 1 over z, right? So we are taking that and that on this side, so z dz minus ay dy is equal to a z square minus s square y square dx. And now we can see that what is this? This is actually the differential of z square minus ay square. See, 1/2 should be adjusted, we are taking that there, and as well there should be 1a be adjusted to this side, so we are writing s square a and we are taking 1a there. So this is equal to s a z square minus s square y square dx. So simply we can write 2 over a d a z square minus s square y square a z square minus s square y square to the power half is equal to dx, and hence we have the solution as, this is half, so that will be actually this is minus half, so that will be half, and 1/2 will be coming down crossing this 2. So integrating, the result is simply a z square minus a square y square 1 over a is equal to x plus another arbitrary constant. So finally this can be written as x plus b whole square is equal to z square over a minus y square, or rather more simply we can write it as x plus b whole square plus y square is equal to z square over a. And as you see, this is a equation of a cone, right? So this is the solution of the given differential equation. In the next class and next day we will solve one by one different Charpit's method. I mean, using Charpit methods we will solve different partial differential equations.